the entropy at inlet and the entropy at exit must be the same. So with this understanding, let's go back to our problem of nozzle, which we had done earlier. So at that time, if you look back, we had specified the pressure and temperature of superheated steam entering the nozzle. We had also specified the final state, the pressure as well as the quality of steam. Now, that was not taking into account the second law of thermodynamics. Now that we have studied the second law of thermodynamics, let us go back and redo that problem. So let's say this is the nozzle. At inlet, so 1 atmosphere is approximately 0.1 megapascal, which means at the inlet you have a pressure of around 6 atmospheres, and at the exit the pressure reduces to around 1.5 atmospheres. So at the inlet the temperature is 200 degrees centigrade and it's entering with 50 meters per second. So then if I expand it adiabatically, then the question comes, what would be the state of the steam at the exit? So the thermodynamic state here is specified by the two variables P1 and T1. If I know P1 and T1, then from the tables I can look up 0.6 megapascal 200 degrees. So 0.6 megapascal and 200 degrees is here. So this is V, this is U, this is H, this is S. So V, U, H and S. So S is 6.9683. And H is 2850.6. Now the expansion here is adiabatic. It says enters an insulated nozzle, so it's adiabatic. If we assume it's reversible, in that case, and we are assuming that it's a steady state, steady flow situation, in that case, S at exit must be same as S at inlet. Therefore, S2 we know that two coordinates uniquely specify a thermodynamic state. So this pressure together with this entropy specifies the thermodynamic state. So what we need to do now is go back to the tables, check for this pressure and find out where is this point where it has entropy this much. So then just thinking it out, it was superheated steam, it is being expanded, so the temperature is coming down because of expansion, because it does work during expansion, so that work comes at the expense of the thermal energy, so therefore the temperature must come down. So if it comes down, will it still remain a superheated vapor or will it enter the saturation region? So then the first thing to do is to check the values of entropy for saturated liquid and saturated vapor at this pressure. So this is the saturation. These are properties of saturated liquid and vapor, the pressure based table. So I scroll down until I come to the point where pressure is 0.15 megapascal. So if you see, this is pressure and these last three columns are entropy. So SF, SG and SFG, all in kilojoule per kg cube. So at 0.15, SF is 1.4337 and SG is 7.2230. So if you look back, when we drew the TS diagram for steam, the at a certain pressure, the entropy increases steadily as you transfer heat to the system, and the material converts from liquid to vapor. So at a pressure of 0.15 megapascal, the entropy increases the specific entropy increases from 1.4337 to 7.2230 as the water changes from liquid to vapor. So for pure saturated liquid, this is the value. For pure saturated vapor, this is the value. If you heat it further, it becomes superheated steam, and then the specific entropy would be higher than this. Now our value is 6.9683, which is less than 7.2230, which means the steam at exit, assuming isentropic expansion, would be in the saturation region, a mixture of liquid and vapor with a quality such that the entropy is same as what it was at inlet. So SF is 1.4337 and SFG is 5.7893. That is what will help us to calculate quality. So at P2, SF is equal to 1.4337 and SFG so therefore S2, this is what the entropy at exit must be, same as what it was at inlet. So then that should be SF plus X2 into SFG. So this is the quality of steam at inlet, at exit. So if I know the quality, I can calculate what is the enthalpy. That will be HF plus X2 into HFG. So at 0.15, these last three columns were for S. These three columns before that are for H. So HF is 467.13 and HFG is 2226. So therefore, so once we know H, we can apply the first law. So this is steady state, steady flow. This is equal to 0 adiabatic. And there's no work done in the nozzle. I'm assuming that changes in potential energy can be neglected. So then so the exit is we have denoted by 2, and the inlet by 1. So this now something which I've been telling you all along and trying to follow as far as possible, that always retain units. Now in this case, it turns out it is important. Why is it important? Let's see. H1 minus H2 would be, H1 was 2850.6 minus H2. H2 is 2595.2. This is in kilojoule per kg plus V1 is 50 meter per second. So now that we have written the units, you can, I presume, make out where the problem is. That kilojoule is not the SI unit. So kilojoule per kg is 10 to the power 3 joule per kg is equal to 10 to the power 3. Joule is Newton meter. So it is Newton meter per kg. And Newton is kg meter per second square into meter divided by this. So essentially what I'm saying is, if you write it as convert this to joules per kg, joules per kg is same as meter square per second square. Now, if you look back in your notes, you will find that Okay, so it was not actually the temperature or the quality of steam which was specified, it was the V2 which was specified. So then this was the actual velocity which was obtained, and what we have now calculated is assuming that the entire process is reversible. So assuming that the entire process is reversible, we get a expected velocity of 716.45 meters per second, whereas the earlier value which was given, it now appears that probably that is what we actually get, because there will be losses in the system. If there are losses in the system, we expect the velocity will be smaller. So then we define something called nozzle efficiency. So the purpose of a nozzle is to produce a stream with high velocity. So it'll produce a jet of fluid with high velocity. So then, how well it is doing it, a measure of that would be what is the kinetic energy we actually obtain, the kinetic energy per unit mass of material flowing out from the nozzle. How much do we actually get compared to what it would be if there are no irreversibilities? So then eta nozzle so the V exit actual square by 2. So this is the actual kinetic energy which you obtain, and VES. So S denotes isentropic. So if I were to assume that the expansion is isentropic, then what is the kinetic energy I would obtain? So if it is isentropic, that means there is no entropy generation. So that would be the ideal kinetic energy. Kinetic energy in the absence of any irreversibilities, but there are actual irreversibilities, friction, etc., which because of which the actual velocity obtained is less. So the actual kinetic energy divided by the ideal kinetic energy, that is the nozzle efficiency. So therefore, for eta n, this turns out to be around 70%. Now, if I see the discussion in the book says nozzles are simple devices with no moving parts. As a result, nozzle efficiencies may be very high, typically 0.90 to 0.97. So either the nozzle which gave us a exit velocity of 600 meters per second was an exceptionally badly designed nozzle, or the problem was a badly designed problem. So if we redo the problem which we had done earlier, the nozzle efficiency turns out to be 70%, but in actual practice, nozzle efficiencies are higher, typically 90 to 97%. So then our actual expansion gave us a velocity different from the isentropic expansion. So then, if you remember, when we derived second law for a control volume, that time initially we had kept a term which is the entropy generation. Now, there are various losses because of which the nozzle efficiency might have decreased. There could be heat loss from the nozzle. There could be entropy generation. Now, since no information is given, if I assume that there is no heat loss, in that case, if I look at this equation, let's say I have steady state. And I assume the expansion is adiabatic. So the difference is that in an actual nozzle, there is entropy generation. So from where will I get it? Earlier, this time, we assume that the entropy remains constant from inlet to exit. Using that, we got the value of the enthalpy. Once we got that, using first law, we got what was the velocity. Earlier, we were given the velocity at exit. Using that, we could calculate what was enthalpy. So then we have to go back and see for that state what is the entropy. For the actual expansion, we had calculated what is the enthalpy, and for that value of enthalpy, we had found that x2 actual was 0.99. So this time it was 0.956, but there it turned out to be higher, 0.99. Correspondingly, S2 actual is equal to SF plus X2 actual into SF. SF Fg. That turns out to be so from this equation S dot gen is m dot into Sc minus Si. So if I move these to the left hand side, this is what I get. So if I plot on a TS diagram, I had steam in the superheated region, expanded isentropically, it would give me quality of 0.96. So it would give me a quality something like this. When I take the real expansion, the quality turns out to be higher. So the real expansion is something like this. So this is the ideal and this is the actual. So as you can see in the TS diagram, the entropy, there is entropy increase in the actual process. Now let's come to something which is more widely used, a turbine. Okay, let me take attendance, but there seems to be a real serious problem with attendance today. A steam turbine receives steam at a pressure of 1 megapascal 300 degrees centigrade. The steam leaves the turbine at a pressure of 15 kilopascal. The work output of the turbine is measured and is found to be 600 kilojoule per kg of steam flowing through the turbine. Determine the efficiency of the turbine. So by now you're familiar with how to use the tables. So I'll not go back and forth. I'll just give the final values. Okay, here it turns out that the tables which we have kilopascals. So that would be 0.015, but it's given for 0.014 and 0.016. So what we do, we linearly interpolate. So then if we want SF, what we do, we take the average of this value and this value. Sorry, this is 0.015. So we take the average of this value and this value. Similarly for SFG, we take the average of this value and this value. So these are values which we see from the table. So taking the average, that gives us an approximation for the value at a point halfway. So it is this row which we require. So then this is the entropy which it has at exit. So that will be so unlike a nozzle where the idea was to get a high velocity, so the cross section areas etc. Designed in such a way that you get a high velocity at the exit. In a turbine, it's not done that way because the main idea is to get work output. So then in a turbine, usually we assume that differences in kinetic energy, so typically the velocity at inlet, velocity at exit are comparable. So, so changes in kinetic energy and potential energy, we assume can be neglected. In that case, assuming steady state, assuming adiabatic. So the work done per unit mass is W dot Cv by m dot. So whatever the decrease in specific enthalpy gives you how much of work output you get from the turbine per unit mass. So that turns out to be and we are given that the actual work output so we define the efficiency, turbine efficiency the actual work output divided by the ideal. So this would be 600 kilo joule per kg. and here you do have moving parts. So is this realistic? Well, the book says typical turbine efficiencies are between 70% to 85%. So this turns out to be in line with what typical efficiencies are like. Now, another device which has moving parts is the compressor. So it could be a compressor or a pump. So when the material being handled is a liquid, we call it a pump. When it's a vapor or a gas, we call it a compressor. So that efficiency, now the work is for a turbine, the work was the output. So in actual practice, you get less of output than what you would get ideally. So the turbine efficiency was defined as the actual work output by the ideal. Now, compressor, the work is the input. So for getting a certain compression, ideally you have to provide a certain amount of work. Because of losses, it turns out that the work which you have to put in is actually more. So then the compressor efficiency is defined as, so this gives you a value less than 1 because the actual work which you'll have to put in will be more than the ideal. And the compressor efficiency is again in the range of 70 to 85%. So component wise, we have seen how we can use the second law of thermodynamics in order to predict, in the absence of irreversibilities, what would be the typical work output or the work output from a turbine or the velocity output from a nozzle. So now we are in a better position to predict the performance of devices. Once we have seen component wise, the next step would be to actually consider an entire system which either generates power or provides refrigeration. So an entire system, a system which provides refrigeration. So we know that if you want to remove heat from a colder to a hotter body, certain work output is required. It cannot occur spontaneously. So then what is the sequence of processes which the refrigerator has to go through in order to provide this, and what would be the performance like? So that we have to see in detail. Similarly, we know that thermal energy cannot be converted completely to work. So what is the process through which thermal energy is converted to work, and how much of it gets rejected to a lower temperature reservoir? So so what are the cycles which generate power? What are the cycles which provide refrigeration? Those are the things which we'll have to um, see in detail. Now we are lagging behind our schedule, but then if I see we lost some amount of time because of holidays, etc. So still it started in around mid-August. Now it's around mid-September, and the semester continues till end of November with puja break in between. So if I say half of the semester can be devoted to thermodynamics, we still have some amount of time. So we'll discuss those cycles from the next class. And I think there is one point which I need to make. How was the exam?
Sir,
Huh.
So, like before coming to that question, I want to make a point, sir. Like you
Yes.
have seen the attendance in today's class actually is very less. The
Huh.
thing is that all the undergrad students of the second year, we are all performing a boycott of classes from Thursday and Friday. I mean, these two
Is it?
classes alone.
Huh. Why? Why?
So because like we have all sent a mail like last week regarding when the institute is going to open and those information, but we are not getting any much clarification for the past few weeks. So we are thinking that another more better action has to be taken. So we are performing this.
Okay. So your main grouse is that institute is not reopening.
Yes, sir, like we have all come to IIT for performing all the we want to learn everything practically, and online semester also it's very difficult for us to learn stuff. And being a student of mechanical engineering, actually it's performed by all departments, and us being student of mechanical engineering, we need the most of our practical work and knowledge and stuff. So we have all decided like all
I see.
departments of Kharagpur, we have decided for the 2 days alone we'll perform boycott and we can see like any decisions being taken by the administration. So
Oh, I
Sir,
see.
if I
Oh,
may
okay.
interrupt here.
Okay. That clarifies the position. But actually, you should see it from the point of view of the teachers also. The main risk is that even now the pandemic is still not under control. And what an academic institute is always worried about, even when research scholars were called, right after that we saw a spike. Because the way people stay in hostel mixing with each other, it's very difficult. We who are more elderly, we stay to ourselves, so there wasn't much of coronavirus going around. But the moment research scholars came, all of a sudden there were quite a few cases. And what any academic institute would be always scared of, if there is even there were infections among the laboratory staff, there were infections among the office staff, and there were infections among the research scholars also. Now what an academic institute is always worried about, if there is even quite likely that if students are called back and called back in large number, then cases of corona would go up. So then the main fear of any academic institute is, if there is even one student death, that gives a very bad name to the institute. That is what anybody in an academic institution would be worried about. So actually my personal view is that the when we reopen, we understand that educational institutes need to reopen, but probably we should start with the day scholars. So if schools open, then in case there is a problem, one can shut down. But whereas if IIT calls students, how will you go back during the lockdown? Because right now there are all sorts of problems. In this region, local trains are still not running. So during a pandemic, going back, that itself is a troublesome thing. So especially in second year, I don't think it should be a serious problem. And you haven't come to IIT, so you don't know what the laboratory classes here are like. Now I have gone through this system through every stage. Like after class 11, I came and joined here as an undergraduate student. I have also done my PhD from this place. Now, the amount of practical training which we got was not really what we had thought we would get. In fact, I don't know whether I should say this, but quite often we found there's one experiment going on and an entire batch of 20 students gathered around it. So none of us actually got to take those measurements directly. This is unlike the laboratory classes in school, where you in school, at least in physics lab, it was one student working on one setup, which is not true in our mechanical engineering. So then I don't know whether you're missing much, because now you have virtual labs. Looking back, some of our actual labs were almost virtual labs. So I think you need a little more patience, especially second years. Okay, let's see how things go, because I don't think second years right now institute is considering. Because the rumor which I've heard is right. One thing which we have heard is that the MTechs will be called, provided there is no surge after the festive season. And then, if that goes smoothly, maybe final year undergraduates may be called. But beyond final year undergraduates, so that is also the second stage. First is the final year postgraduates, because there are people who have never seen the institute and are going to pass out without ever seeing the institute. Now, whether it's important to see the institute, I don't know, but the aim is to get them. But they are waiting after the festive season how things turn out. So at the moment, I think you have to be realistic. None of the schools have yet opened. And in your case, at least online teaching is going on, because in schools, in theory, online teaching is going on, and urban schools probably the online teaching is going on. But if you move away from cities, like we are staying in a place which is away from a city, so if we see the people who live outside our college campus, those schools are closed for the last 1.5 years, and although whatever they may say, online teaching is actually not going on. On the other hand, here at least the theory subjects we are teaching online. So I think you need a little more patience. Is the boycott continuing tomorrow also?
Yes, actually, like if you see the other IITs, like they have all like tried. I mean, they have opened for second years also. Basically, we are the freshies and we are in second year. Basically, they should open for us as along with MTech students. Like what other IITs have done is like for other IITs also the schools are not have not opened in their state also. So what they have done, they have called all the students and they made them stay for like about like 4 weeks or so, and they've seen that there are no spurge of coronavirus. So they are like stay. They let them stay throughout the entire year. So like what we are trying to say also, like let them call us, and we can stay there. We can arrange for some mode of transport. Like only once you have to come and go, we can get special permission also from state as well. Actually, those permissions are also valid, and we can also come if the institute saying okay, if there's a spurs in the case, okay, we have to go back to our own state, we can do that action also. But we have seen like about 300 students of not 300, about 169 students about of second years are in IIT for because of resource constraints, and third and fourth years also are present there. So totally about 600 students, and there haven't been any like cases as well. So what we are trying to say is we can increase the number twice and thrice, because and we can they can call us back. So
No, in fact, I believe such an attempt is going on, but people are doing it in stages. Instead of calling everybody, they are prioritizing. So when they prioritize, the final years get first preference. So then right now, I think you have to wait and see, because there are certain other things. Like Kharagpur is away from a city, so we have always had this problem. You would not be aware because you have not come to campus so far, that in Kharagpur, medical facilities are not as good as they are in cities. So in a city, in case there is an outbreak, the authorities will be in a position to take care of it. Whereas if it happens in Kharagpur, it will be difficult. So that is why people are going cautiously.
Okay.
Okay, so we'll close here.